But Bobby, David.
Yeah.
Alright, so let's see. Go ahead, DJ, you do experiment.
Alright, good afternoon. Welcome to Math and Modeling Methods. I haven't finished grading the exam. I started. The exams, I'll have them here on Thursday. I took them home, but the homework might take a little more than that. So I'm gonna wait because I'm trying to hire a TA to help me with the homework. Until we find that person, hopefully within a week or so, we'll have a grade for the homework. But you can pretty much assess where you are at with the homework grade because I posted the solutions. And I am obviously a lot less rigorous at grading the homework than I am with the exam. Okay, are there any questions up until now? Any questions about the exam? Any assessment on your side? Feedback? What do you think? I noticed one thing that nobody turned it in before the time, so I was afraid that almost nobody had finished the exam, but then I noticed that most people finished and that we were just reviewing your results. So I think from that standpoint, I didn't over-design it in terms of size. Any other comments? All right. Well, exam number 2 is going to be take home, so the time stress is going to be taken away. Mostly because the second part of the semester, we're going to deal with differential equations, mostly ordinary differential equations. We're going to talk about, first we're going to do a review of what you already know about differential equations, and then we're going to move to differential equations that you did not handle when you took undergraduate differential equations, such as variable coefficients differential equations or nonlinear differential equations, even systems of ordinary differential equations. And then we're going to look into how to solve these analytically, if possible, and then what numerical approach can we take to actually arrive at a solution or arrive at an approximation. And well, this is mainly the reason why exam number 2 is take home, because there will be some computational exercises. Yes?
How does that work? I know it's take home, but you give it to us like on a Tuesday, you just do it Thursday?
Yeah, exactly. I give it to you on the Tuesday where the homework is due, or when the homework is due, and then you bring it to me on Thursday.
Ah, okay.
Yeah, so we have a couple days to solve it.
Yeah.
48 hours. And so is the final. The final has a section that's take home, but then I give you a full weekend to work on it. Yes?
Do we have the class on the Thursday that it's due?
No. Okay. No. Okay, so you can use all the way up to the end of class time to turn it in. Okay, so can you do me a favor and turn off the light, please? Thank you. So this will be lecture number 10, I think. Yes. Modeling methods. So we're going to start with a review of ordinary differential equations, and this is something of all use for us. So ordinary differential equations. So we call these ODEs. And what makes an ordinary differential equation ordinary? You know, what do we call them ordinary, as opposed to partial. That's it. An ordinary differential equation is one where there's only ordinary derivatives, okay? No partial derivatives. So it's basically an equation whose solution is a function of a single variable, okay? Well, that's the difference between a differential equation and an algebraic equation. An algebraic equation, the solution is a number or a set of numbers or a range of numbers. In a differential equation, the solution is a function. I guess this is something that most math professors fail to say when they're covering differential equations. It's just an equation where the answer is a function, okay? And so that's we express it through derivatives. Yes, I think we do the opposite. Thank you.
Yeah, that's better, right?
And again, ordinary is because there is no partial derivatives in it. So we're going to start with those functions who are just functions of a single variable. In general, an order n, linear, non-homogeneous, ODE is given as coefficient Cn of time of d, the nth derivative of y with respect to t to the n, plus a Cn minus 1 coefficient, could be a function of time, times the n minus 1 derivative of y with respect to t to the power of n minus 1, plus C1 times the first derivative of y with respect to t. I'm sorry, the C1 could be also a function of t, plus C0, who could be also a function of t, times the zero derivative of y. The zero derivative of y is just the function y, and it's equal to a right-hand side function gt. That is a general expression for an nth order ordinary differential equation. Okay? What makes it non-homogeneous is the right-hand side function. Here, if this right-hand side function is 0, we call this equation homogeneous. If the right-hand side function is something different than 0, even just a constant, then we call this equation non-homogeneous. Alright, so we call it linear because it is a linear combination of coefficients times different order derivatives of the function. Okay? As soon as you see the function multiplying itself, or the function multiplying one of the derivatives, or one of the derivatives multiplying another one of the derivatives, or anything square, dy squared, then it ceases to be linear. And then the implications of that are very serious, because nonlinear equations do not necessarily have a solution, and if they do, that solution might not be unique, and there might not be a method to get to it. Okay, so in general, if the equation is linear like this, at least it's guaranteed that the solution exists. The solution exists, and the solution is unique. That means there's a single function that's the particular solution to this equation in a set of conditions. Okay, so there's a guarantee that it exists. However, there's no guarantee that we can have a method, a general method to get to it. All right? But if there's a guarantee that it exists, at least we can attempt either analytical or numerical methods to get to the answer. Okay? When we talk about analytical methods, are methods that will get us to the function y of t. Will get us to the algebraic expression of the function of y of t. Those are analytical methods, and we call those exact. Okay? Numerical methods are those who would get you to a discrete set of values of y with respect to t. So instead of attempting to find the algebraic expression of y, you either attempt to get a different expression in terms of series, or attempt to get an expression in terms of distribution of points, or distribution of values of y, discrete distribution of values. That's the difference. Instead of finding the function itself, well, you find some sort of distribution of y as a function of t, and you're okay with that. That's enough, because at least I know the behavior of y with respect to t. That's constrained by this equation. So we call the COTs all the way to CNT coefficients. These are the coefficients, and these are the coefficients that linearly relate the different variables or the different order derivatives. So if Ci of t is equal to a constant for all I from 0 to n, then the ODE is constant coefficient. So a constant coefficient, ODE, is one where the coefficients are not functions of the independent variable. Well, otherwise, if at least one of the CIs, if at least one of the coefficients is a function of time or it's a function of the independent variable, again, it doesn't have to be time, and y doesn't have to be y, it's a dependent function of an independent variable. So if at least one of the c's happens to be a variable, it happens to be a function, we call this a variable coefficient ODE. Okay. Now if GT is equal to 0, the ODE is set to be homogeneous. All right? Homogeneous ODE. And again, there are some very particular implications to the fact that an ODE is homogeneous. Oh, let me not take this away. All right. So let's talk about the superposition theorem. And this is a very important theorem. It's very simple, but very important, and we'll make good use of it later, because it's what's going to allow us to build solutions of difficult equations. So it just happens that if y1 of t and y2 of t are both solutions of the same linear homogeneous ODE, then y3 of time equals to some constant y, any constant y, a times y1 plus b times y2, any constant b times y2, is also a solution of the same ODE. Okay. Again, it's very simple. If you have a linear ODE, and it happens to also be homogeneous, and then you find by some method that y1 could be an answer to that, or a solution to that equation, a general solution we call it, and then we find that y2 could also be a general solution, then a linear combination of the two, through constant coefficients, it is also guaranteed to be a solution of the same equation. That might seem very useless, but you will see how we use this in the future to actually create solutions out of series. Okay? So we'll create solutions out of infinite series, because that applies for any number of solutions, y1 all the way to y infinity. So if we can come up, if we can think of functions, an infinite number of functions who could potentially be solutions or answers to a differential equation, and we can linearly combine them to make up a more complex solution, which we call yn, and then just try to find the coefficients. And it's kind of challenging to find an infinite number of coefficients, but there are methods to get to them. All right, so let's start with first order ODEs. First order ODEs. So we'll devote some time today and next class just to talk about first order ODEs. These are problems in physics and engineering and science that can be governed by the fact that the derivative, the first derivative of a function, could be proportional to the function itself and some other functions, okay, and some other variations. Now we're not talking about, notice I'm not classifying this as a linear, homogeneous, or anything like that. Okay, I'm just saying first order ODEs. The only requirement is that the highest derivative of the equation is first order. It can actually be nonlinear, and we're going to attempt to find a way to solve these. So in general, a nonlinear first order ODE can be written as. I'm going to write it slightly different than the general form that I wrote before, because this one is allowed to be nonlinear. So we really don't know what the power of y is, or if y is maybe the argument of a transcendental function, or if it's inside an irrational function like a square root. It's allowed. Okay, this is a general form. Some given function f that has some variability with respect to y, some variability with respect to t, with an initial condition we call IC, such that y at time equals 0, it's some y0, some given value y0. So the ODE above and initial condition is a set that pose an initial value problem. This is what's called an initial value problem. Anytime there is a differential equation, which we call the governing equation, that's the equation governing the problem, and an initial condition or a set of initial conditions, we call that an initial value problem. That's it. Okay? Now, before attempting to solve these equations, let's try to see some examples of cases where I give you the equation, I give you the answer, and we can verify that that's indeed the answer to that equation, or the solution. So, for example, verify that the following is a solution to the given ODE, and find the particular solution. To the given initial condition. Okay. So if I give you dy dt plus y is equal to 1, how can we classify that equation? It's linear, see? The y dt is not square or anything like that. Y is not square or anything like that. It's a constant coefficient or variable coefficient? Constant. There's a 1 multiplying the y dt and there's a 1 multiplying y. Okay? It's linear. Constant coefficient. Is it homogeneous or non-homogeneous? Non-homogeneous. The fact that there's a number different than 0 makes it already non-homogeneous. Okay? And it's a first order ordinary differential equation. With solution c e to the minus t plus 1. This is called the general solution. We call it general solution because it is actually a family of solutions. It's not a single one. It's a family of solutions. It would work for any value of c. Any value of c you pick will still be a solution to that equation. So it doesn't solve the initial value problem, it just solves the differential equation. Now when we combine the general solution with an initial condition, y0 is equal to 2.5, then that would lead to a particular solution. A particular solution is a unique, the particular solution for the problem. So this is a first order, linear, constant coefficient, non-homogeneous ODE. All right? So we could rewrite this equation in the general form. dy dt is equal to f of y and t. If we write it in that form, then f of y and t is who? 1 minus y. Is that clear? All right. So all we need to do to make sure, verify that this is an answer, to verify, check that left-hand side is equal to right-hand side. That's all, right? So what we do is just take left-hand side is equal to dy dt, which is equal to d dt of c e to the minus t plus 1. What would be the time derivative of that? Negative c e to the minus t. Okay, so that's the left-hand side. Right-hand side is equal to 1 minus y, which is equal to 1 minus c e to the minus t plus 1. And then right-hand side is equal to minus c e to the minus t. There we go. So that is indeed a general solution. So therefore, y of t equals c is a general solution. Let's call it the general solution. Which is semantically incorrect to say that it's the general solution because it is actually a family of solutions. Okay? Now the particular solution will be found after we apply the initial condition that says that y of 0 is equal to 2.5, which is equal to, well, we just replace t with 0. So e to the 0 will be 1, and then c will be equal to 2.5 minus 1, and therefore c will be equal to 1.5. And therefore, y of t equals 1.5 times e to the minus t plus 1 is the particular solution. And now we can say the particular solution because it's a single one. But that's only possible because the original equation was linear. Linear equations are guaranteed to have a particular solution once an initial condition is provided. Okay? Nonlinear equations might not even have a solution, and if they do, it might not be a single one. All right. Let's do another one. B. Let's do y dy dt is equal to t with y of t given as or such that y squared minus t squared is equal to c. Okay, it's given in implicit form. And with an initial condition of y of 0 is equal to 1. Okay, let's classify this equation now. The highest derivative in the equation is the first derivative, so therefore this is a first order ODE. Is it linear or nonlinear? Linear or nonlinear? Nonlinear, because we have y multiplying dy dt. Okay, anytime a derivative multiplies itself or anybody else or any of the other derivatives, including the zeroth derivative, which is y, or it is inside of a square root, or is the argument of an exponential function, or logarithm, trigonometric function, it really doesn't matter. As long as we don't have a linear combination of y and its derivatives, then it ceases to be linear. So this is still a first order, nonlinear, Now we cannot, the concept of constant coefficient and variable coefficient now is irrelevant. Once the equation is nonlinear, there's no point on saying whether it's constant coefficient or variable coefficient. As a matter of fact, the coefficient will be variable because y will change as a function of t. Well, we can say that this is non-homogeneous, ODE, because the function on the right-hand side, the independent term, is different than 0. So we can rewrite this in the general form, dy dt is equal to f of y and t, such that f of y and t is what? Okay, t over y. All right, so now we're going to compare, we're going to check whether this is the general solution. Again, to verify, check that the left-hand side is equal to the right-hand side. Okay, such that we can get from here that y of t is equal to plus minus the square root of c minus t squared or plus t squared. Right? All right, so the left-hand side is equal to dy dt, which is equal to the derivative with respect to time of plus minus the square root of c plus t squared. Again, this is an exercise of verification. We are given the solution, just to verify whether it is right or not. Okay, so what would be the left-hand side? What is the derivative of this? Remember? This is a function to the power of 1/2. That would be 1/2 times the function to the power of minus 1/2 times the internal derivative, which is 2t's, right? So the 2 on the t, where the 1/2 will cancel out. So we'll have plus minus t divided by the square root of c plus t squared, right? And the right-hand side, which is equal to t over y, is equal to t divided by plus minus the square root of c plus t squared. This is y. So the right-hand side is equal to plus minus t divided by the square root of c plus t squared. So they're indeed the same. That means that that given general solution satisfies the differential equation. So therefore, y of t equals plus minus square root of c plus t squared is the general solution. Again, it's not a particular solution, or it's not the particular solution, it's a family of possible solutions. For any value of c, that would be a possible solution, in addition to the plus and the minus. Alright, now we use the initial condition that says that y of 0 is equal to 0, and that would mean that 1 squared minus 0 squared is equal to c. So c will be equal to 1. Right? That's from the original implicit form of the solution. And therefore, y of t should be equal to plus minus 1 plus t squared and this is the particular solution. So that is a function that satisfies both the original differential equation and the initial condition. When you evaluate at t equals 0, you should get y of 0 equal 1. Okay? Now, for some reason, one of them, both satisfy the governing equation, but only one of them satisfy the initial condition, right? Even though we found that c is equal to 1, we plug in the c, the plus minus stays there, but when time is equal to 0, we can only have the plus sign because the initial condition has to be 1, not minus 1. But also notice that particular solution is not unique. All right. So these are easy cases of equations with given solutions, general solutions, and just a matter of implementing the initial condition to find the particular solution. Now let's learn about methods on solving first order ODEs. Again, some of which might be old to you. And the easiest ones for general first order ODEs, again, when I say general, they could be nonlinear, is when they're separable. So if the equation is separable, then it is easy to get to an answer. So if the ODE dy dt of f of y and t is such that it can be written as some p of t dt equals to q of t, q of y or dy. So somehow that function f is such that we can take the y and the t terms and separate them. One to the right hand side and the other one to the left hand side, so that no y's are left on the left and no t's are left on the right. That will be a very specific case of equations. Then the integral, if you take the integral of both sides, equals to the integral of q y dy will directly yield an implicit form of the solution y of t. Implicit meaning that it's not necessarily written as y of t equals to some function of t. You might have y in combination with t's, but at least you have a relationship of y and t. Okay. So that's the first case. And if it happens to be separable, then solution is readily available and simple. So given, let's say, dy dt plus 5t to the fourth y squared equals 0, with initial condition y of 0 is equal to 1. At time equals 0, the solution must be 1. So find y of t. All right, let's classify this equation again. It's first order, right? The highest derivative is first. It appears it's variable coefficient, although that's irrelevant because the equation is nonlinear. See? We have y squared. It will automatically make it nonlinear. But it's homogeneous. Okay, that doesn't help any because once the equation is nonlinear, everything else goes down the drain. Okay? So, this is the first order nonlinear, homogeneous, ODE. We can write it in the form dy dt equals to f of y and t, such that f of y and t is just simply minus 5 t to the fourth y squared. Right? I'm just rewriting it, sending everything else to the right, and isolating the dy dt. There's no particular benefit on writing an equation this way. That's a general form for a first order ODE, be it linear or nonlinear. However, when we get to numerical solutions of ODEs, this is going to be the form of choice. You can write it this way, there'll be advantages. All right. So let's attempt to separate. So notice that if dy dt is equal to minus 5t to the fourth y squared, we can attempt to separate it and be successful if we just say 1 over y squared dy is equal to minus 5 t to the fourth dt, where this is q of y and this is p of t. So this one is separable. This is the same equation here, just written slightly different. And if the left-hand side is equal to the right-hand side, which it is, because this is the equation given to us, then the integral of the left-hand side should be equal to the integral of the right-hand side. All right, so that means that the integral of 1 over y squared dy should be equal to the integral of minus 5t to the fourth dt. All right? So, what's the answer to the left-hand side? What is the integral of 1 over y squared dy? Y to the minus 1. This is y to the minus 2, right? That will be y to the minus 1 divided by minus 1, right? And on the right-hand side, that's a polynomial, that's easy, so that would be minus 5 times t to the 5 divided by 5. That would be minus t to the 5. Plus a constant of integration. Okay? Both sides yield constant of integration. And we just collapse those two into a single constant of integration. We call it c, put it on the right-hand side. Okay? That's what makes a general solution. So if we multiply the whole thing by minus 1, and take the inverse, then y of t is equal to 1 over t to the 5 minus c. This is again the general solution. It's a general solution because it's a family of solutions. Any value of c would satisfy this equation right here. You plug in this in here and plug it in on the right hand side, negative of these, you get the same thing. Okay. With initial condition given as y of 0 is equal to 1. Notice that the answer happened to be arrived at in explicit form. That's not going to be the case all the time, right? It just happens that when we integrate the left-hand side, we got y to the minus 1, so we can easily invert that and make it y is the inverse of the right-hand side, okay? But not all the time, that will be as simple as that. Sometimes the solution, it would just be an implicit form, where we have y to the third power plus y to the second power minus t to the fifth power is equal to a constant, something like that, okay? It just happens that this time we could find an explicit form. Is that clear? But still an answer. Whether the solution is implicit or explicit, it is still an answer. Now, it appears also that this solution is unique. Well, once we fix the initial condition, we found a unique family of solution which will yield to a unique particular solution, and that's not the case all the time for nonlinear ODEs. Remember that nonlinear ODEs do not necessarily have an answer, and that answer might not even be unique. It just happens to be the case in this particular example. So when we apply initial condition, we say y is equal to 1, so 1 will be equal to 1 over 0 to the power 5 minus c, and that would be that c is equal to minus 1, and therefore y of t is equal to 1 over t to the 5 plus 1 is the particular solution. Okay. So that's it. That's all we're going to do about separable equations, because it's very unlikely that a given first order differential equation that governs a particular problem happens to be separable. Okay? It doesn't happen all the time. Imagine this equation right here. If we just put a 1 on the right hand side, you just put a 1 on the right hand side, then how would you separate the y's to one side and the t's to the other side? Okay? It's not separable. Just putting a 1 here will make it not separable. And it just happens that this one is nice and separable. So the second types of equations that we are going to study are the exact first order ODEs. Alright, so that's the second check. We first check whether the equation is separable. If it is not separable, if the ODE is not separable, and it is written as, let's say, py, comma t dt plus qy, comma t dy equals 0. Okay, we take the equation that happens not to be separable. Notice that those p's and q's are both functions of y and t. Okay, we were not able to pull all the t's to one side and all the y's to the other side. So we ended up with a form like this. Then if dp dy is equal to dq dt, notice the function that multiplies dt when we differentiate with respect to y is equal to the function that multiplies dy when we differentiate with respect to t, then this equation is exact. Then the ODE is set to be exact. Okay. Alright, so then we have a differential equation. We have to rewrite it in this particular form where p, some function p multiplies dt, some function q multiplies dy. If the partition of p with respect to y is equal to the partition of q with respect to t, then we say the equation is exact. And what is the benefit of that? Then, therefore, a function t equals to c can be found as u of y of t is the integral of p of y on t with respect to t. Now we take the integral of the function that multiplies dt, we integrate with respect to t, and that should yield, when we integrate this with respect to t, that should yield a constant of integration that is a function of y, because this is a partial integration with respect to t, so any function of y will be a constant of integration. We'll do an example. And simultaneously, uy of t is also equal to the integral of q with respect to y plus a function g of t. We're integrating with respect to y, that's a partial integration. It's a partial, it's a function of two variables, so it's a partial integration. Any function of t can represent the constant of integration in this integral. The function, the expression uy of t equal to c represents an implicit solution to the ODE. But that's only possible when the equation is exact. Because when the equation is exact, these two integrals will yield the same exact solution. Okay? Any function of y and t combined, the results out of this integral will be found on the second integral simultaneously. Notice that this is the same u appearing on both expressions. Okay. Example. Okay, given in this case we're not given an initial condition, so we're just to find a general solution. So let's say dy dt equals to minus 2t plus e to the y divided by t times e to the y. Well, that's definitely a nonlinear ODE, right? Because notice that y doesn't appear on its own. It appears as the power of an exponential function. Okay? So it is definitely nonlinear. It's a first order nonlinear ODE. So this is a first order nonlinear ODE. So let's rewrite it. We're going to rewrite it in such a way that there's a function. First, can we separate it? Can we separate that function? Is it separable? Such that we have, bless you, q of y dy is equal to p of t dt. We can attempt to do so. Take this e to the y, multiply it here, but then we'll leave. We'll have an e to the y on the right hand side. Just try to bring that in. The answer is no. No. The next check is it exact? So now we need something that looks like p of y and t times dt plus q of y and t times dy equals 0. We need to rewrite that equation in this form. Okay? So would say we can take that equation and say that this would be 2t plus e to the y times dt plus t times e to the y dy is equal to 0. Notice that that's not the only way that we can write this equation in this form. Right? Okay, we can divide the whole thing by t, and then this function will be slightly different, and this function will be slightly different. Right? We can divide the whole thing by e to the y. We'll have a different form. But that's one way, right? That's one way that we can take this equation and write it in this form. Now let's check. If again, this is p of y and t, and this is q of y and t. So is dp dy equal to dq dt? That would make it exact. So let's see. dp dy would be equal to the derivative with respect to y of 2t plus e to the y. And how much is that? What is the derivative of 2t? 0, because it's a partial derivative. Derivative of ey? E to the y. dq dt is equal to d dt of t times e to the y. What is that? E to the y. So yes, they're equal to each other. So now ODE is exact. All right. So what do we do? And we can attempt a solution of the kind where simultaneously u to of y and t is equal to the integral of p with respect to t. That would be 2t plus e to the y with respect to t. And simultaneously, that should be equal to the integral of t to e to the y dy. And let's see. So what is the integral of 2t with respect to t? T squared. What is the integral of e to the y with respect to t? T times e to the y. Right? Okay. Now there's a constant of integration plus, we're going to call that f of y, because any function of y is a constant when it comes to t. That means that if I differentiate this, whatever f of y is, I will get this. Right? That's what the definition of an integral is. Now let's integrate this with respect to y. What do you get? T to e to the y. That doesn't change. Okay, it's just a constant times e to the y, and we're differentiating and integrating with respect to y. It's just e to the y times that constant. Plus any function g of t means a constant on a y integration. Because if I take the derivative of these, whatever g into the t is, I will get back this. Is that clear? Alright. So notice that because the equation of it is exact, the functions that are combinations of t and y are common in between the two solutions. These are simultaneous solutions to the same thing. This function of t that we're looking for should appear here. There it is, t squared. And this function f should appear here. And there's a 0 there. Therefore, u of y and t is equal to t times e to the y, not twice t times e to the y. that is a solution, t times e to the y, is u plus t squared. And that is equal to a constant c. That represents a solution of the equation. So therefore, t times e to the y of t plus t squared is equal to c is an implicit general solution. It's an implicit general solution. It's implicit because we don't have an algebraic form y of t equals to some function of t. It is embedded in the function in there. But that's okay, because that is a relationship between y and t. It is an answer. It really doesn't matter whether we can get to an explicit form, it's still an answer. It just happens that in this case, I think we can get to an explicit form, right? We can solve for y because it appears only one in one of the terms. So it's a good indication that we can attempt to get an explicit answer. So we can say that e to the y is equal to c minus t squared divided by t. And therefore, y of t is equal to the natural log of c minus t squared divided by t. And this is an explicit general solution. Still general because there's a constant of integration c. But it's explicit because now we have the algebraic form of y as a function of t. Now you can check, take that function and plug it in the left-hand side, plug it on the right-hand side, and you'll see that you get the same thing. Is that clear? Okay. So given a first order ODE, first thing we do is check whether it's separable. So if it is separable, great, because we can get an answer very easily. If it's not separable, the second thing we check is see if it's exact. If it is exact, great, because then we can get an answer very easily. We can just find that u. And the third check is, well, if it is not separable and it's not exact, we attempt to make it exact. And that's through the use of an integrating factor. So an integrating factor is nothing but a made-up function that we use to try to make a differential equation exact. So we take the differential equation, multiply the left and the right by something, so that the resulting form is an exact differential equation. That's possible. Okay? So that's called an integrating factor. So given the non-separable first order ODE, written in the form already let's assume that we've already written, it is always possible to write it in this form, okay? Notice it's not separable, so this is not just a function of t, and this is not just a function of y. It happens to be written already in that form, which is always possible again. And it turns out that when we take the partial of p with respect to y, that doesn't yield the same thing as taking the partial of q with respect to t, and therefore is not exact, and therefore u of y and t cannot be found directly. The implicit form of the solution as an integral of p and as an integral of q cannot be found directly. So what we do is we seek a function f of y and t such that, so when we multiply the given equation through by f of y and t, so that would lead to f of y and t times b of y and t dt plus f of y and t times b of y and t, sorry, cube dy is equal to 0. So we're looking for a function. We don't know what it is, but we're looking for a function that when we multiply it through, it turns out that dy of fp is equal to d dt of f cubed. And now this new equation is exact. Alright, now the problem is finding that function. It's called an integrating factor because at the end of the day that function will be an integral of something. So let's try to find f. Let's try to find f of y and t. So what we're going to do is we're going to take those product derivatives there. So this will be f times dp dy plus p times df dy is equal to f times dq dt plus q times df dt. So I just took the chain rule on the condition that the function is exact, or that the equation is exact. So now we have this equation for f of y and t is usually more complicated than the original ODE. Okay, so we went backwards because now we formulated a problem of finding f. See, now f is part of a differential equation. This is a partial differential equation for f. P is known, Q is known. So now we have a partial differential equation to find f, which is more complicated than the original ordinary differential equation. Okay? The equation for f is usually more complicated than the original ODE. So what do? However, in some cases, we can restrict f to be a function of a single variable, i.e. f of t or f of y, and still find an exact expression. Okay? For instance, let f be f of t only. So let's just make it a function of time and not a function of y. If we make it an f of t, what would happen is that in this expression, these will go away, right? Because the f dy is 0. So let's rewrite this. So we'll have f, now we're going to be f of t dp dy plus p times d dy of f of t is equal to f of t dq dt plus q times df of t dt. Alright? The derivative of f of t with respect to y goes to 0. Because if it is a function of time only, then the partial with respect to y will vanish. So now we can just take f of t here as a common factor. That would be dp dy minus dq dt is equal to q times df dt. But the partial derivative of f with respect to t is now a total derivative of f with respect to t. Because f is just a function of time. So partial derivative doesn't have any meaning. So I can now separate this, and this will become df of t over f of t is equal to 1 over q dp dy minus dq dt times dt. Right? Just rewrote the whole thing. And now if this one is equal to this one, then the integral of these is equal to the integral of these. Right? So now the integral of these is equal to the integral of these. And therefore, the log of f is equal to the integral of 1 over q dp dy minus dq dt dt. And therefore f of t is equal to e to the integral of 1 over q dp dy minus dq dt dt. And this is the integrating factor. But, okay, if we find f of t, then we multiply times the original equation, here and here, and then the resulting equation will be exact. Do you see a problem with these? Huh? Well, not really. We have an expression for f of t. All we need to do is take the partial of p with respect to y, the partial of q with respect to t, divided by q, and integrate that with respect to t. But the resulting expression here has to be just a function of t. And the chances for that are very slim. Whatever function of, whatever p you have and whatever q you have of the original equation, when you take these partials and divide it by q and integrate with respect to t, all the y's have to cancel out. Otherwise the trick didn't work. The original trick of making f just a function of t didn't work because the expression that we found at the end is not just a function of t. So this expression must be just or exclusively a function of t or the integration factor f of t to be valid. Otherwise, it's not going to work. So it is not a general solution method. Again, if it were, then we can take any equation, because we can take any first order equation we want and write it in this form. And if this will work all the time, then great. But it just happens that we made an assumption to make f of t just a function of t. and we ended up with these as a solution. So that has to be a function of t. The y's have to cancel out. Otherwise, it's not a valid integration factor. All right. Any questions? That's it. So we'll continue with first order ODEs. On Thursday, we'll talk about numerical solutions, and then we'll go over some examples. And that's it. See you on Thursday.